Okay.
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 Let us begin our seminar. And it's my pleasure to introduce our speaker, Professor Maria Rosaria Lancia from the University Sapienza in Roma. Please.
So first of all, let me thank Sasha and Daria for inviting me to this to give this seminar, and I'm very happy to meet both of them since a long time that we don't see together. Okay, so the topic of my talk will be on non-local Ventzel problem in irregular domains. And I know that this topic has famous papers due to the Russian school, and in particular to Sasha and to Daria and to many other people. So let me briefly remind, since I don't know all the audience and the expertise of the audience, some basic facts. Okay, so usually Ventzel problem are heat type equation in a given bulk Q, where L is the operator governing the diffusion in the bulk Q, coupled with the heat equation, let's say, also appearing on the boundary in the boundary condition. So we are asking that this heat type equation is also solved on the boundary of our bulk of our domain Q. And here, typically, the operator L on the boundary plays the role of a Laplace-Beltrami operator. And then here, by theta, I will denote a non-local term, which can have a different expression, and we shall discuss later on. Okay, so the main references when talking about Ventzel problem go back to the probabilistic paper due to Feller and Ventzel, and then to the wonderful survey due to Apuzhnikaya and Nazarov on Ventzel problem. And then there are also some results due to the Italian school of Favini and Arendt, Metafune, Pallara, then Goldstein, Ruiz, Goldstein, Romanelli, who were attacking Ventzel problem more on the side of a semi-group approach. And then recently, there are some nice papers due to Apuzhnikaya, Nazarov, Palagashev, and Soktova, focusing on Ventzel problem where the assumption of the coefficients of the operator are very, very weak. And please forgive me if I have forgotten somebody and to mention somebody and some other papers, but these are the main ones that I could find in my research. Okay, so our results are mainly focused on irregular domains. So in studying Ventzel problem in irregular domains. And to understand why we are focusing our attention on irregular domains, one has to be aware of the fact that the Ventzel problem often arise as limit in some homogenization problems, and they have they have a strong physical motivations and real world applications, and that's why we shall be interested in considering domains possibly with irregular boundaries. But before going ahead, let me fix what will be for us an irregular domain. So for me, an irregular domain will be an epsilon delta domain with the boundary at this set. Roughly speaking, an epsilon delta domain is the domain which cannot have neither outgoing or ingoing cusps. And asking that its boundary is a this set amounts to ask that there is a measure, a Borel measure, mu, supported on this set, whose volume of the balls has a polynomial growth. So it goes like R to the power D, And typically this D, for instance, if we consider the snowflake two-dimensional domain, it's an example of an epsilon delta domain whose boundary is a D set, and this D, exponent D, is nothing else than the Hausdorff dimension of the set. And as we shall see, it is a non-integer dimension. Okay, why we are making these assumptions? Because, of course, for when we have an epsilon delta domain with a boundary, a D set, we can have immediately, due to the theory of Johnson, Wallin, and Tribble, trace theorem, for instance, for functions which are in WSP or Q. So the typical trace space of functions in WSP is the so-called Bessel space BPP alpha, where the smoothness index alpha is given by S minus this difference. Usually in the Euclidean case, when the dimension of the boundary is 1, this numerator is nothing else than 1. So we are making these assumptions in order to have these trace theorems. Okay, then in view of our goals, we shall make another assumption on omega. We shall assume that omega can be approximated in terms of an exhausting sequence of bounded Lipschitz domain. These are the underlying assumptions in all what I'm going to tell you. Okay. So just to recall where do Ventzel problem arise as a limit of homogenization problem, let's consider this simple case. Suppose that we are given with a two-dimensional domain Q, and we want to solve the heat equation Q, and here eta Q is the heat conduction of the bulk, coupled with another heat equation in this thick layer Qi, whose width is 1 over I, and it has a thermal conductivity at I. Then we have homogeneous boundary condition, and on the interface, we have some other conditions, continuity of the temperature U across gamma 1, and jump of the normal derivatives across gamma 1. So if we want to model highly conductive thin layers, we want to see what happens when the width of the thick layer vanishes, and at the same time, the conductivity of the layer goes to infinity. So we shall consider the limit of the thermal conductivity of the layer times its width. According to whether this limit is finite, 0, or infinite, we end up with different limit problems. And moreover, we shall take into account also the behavior of Ci. Ci is the thermal capacity of our layer, time it's always the width of the layer. So if this limit is non-zero and the limit of the thermal conductivity times the width is finite, we end up with a Ventzel problem in which, as you can see, in the boundary condition appear, let's say, a tangential Laplacian, a Laplace-Beltrami operator. So in our framework, the Ventzel problem model the heat propagation across highly conductive thin layers. But there are also some other different frameworks where you can find Ventzel problems. For instance, weather wave theory. In electrostatics and magnetostatics theory, there is a famous paper by Pamilla Sanchez Palencia. In hydraulic fracturing, and also they appear in some effective boundary condition when considering thin ferromagnetic layers. So why to replace smooth layers with very irregular layers like fractal boundaries? Because in principle, what happens when considering the physical phenomena which describe this Ventzel problem is that the heat starts diffusing inside the domain, and then it's captured, mainly captured by the layer and starts diffusing within heat. So in principle, for physical applications and real-world applications, one could think of keeping fixed the thermal conductivity of the layer and enhance the absorption effects of the layer by increasing the surface. That's why we were interested in considering Ventzel problem in an irregular domain, for instance, with a fractal boundary. Okay, so what is our approach when studying this Ventzel problem? Usually, the first step is to prove well-posedness result in the case of a regular domain omega, and then to consider suitable problems, corresponding problems, which we call Pn, in the corresponding approximating domains Pn. Then, after proving well-posedness results in this case, our main goal is to study the asymptotics. It is to study, to analyze, to investigate whether the limit fractal solution can be approximated in terms of smoother solutions, the solution that we shall call the prefractal solution. And this has an interest in itself, but is also crucial in view of considering numerical approximation of the problem, of the limited fractal problem. Actually, what we can do usually is to analyze the regularity of the solutions of the approximating problems. And in certain situations, as we shall see, one can obtain optimal a priori error estimates for the numerical approximation of the solution. What is still an open problem is to prove that the discrete solution, numerical discrete solution, actually converges to the limit fractal 1. So here it is a very difficult problem, which is still open in the framework of Ventzel problem. So this is our general approach that I will try to discuss in some situations. So we shall use a semi-group approach, and this will be clear later on because it's crucial in order to study the asymptotics of the problem. And usually we shall consider two types of non-local problem. Non-local problem when we consider fractional time derivative, or when we consider a usual time derivative, but the operator A is of non-local type and encodes, of course, Robin or Robin-Ventzel boundary conditions. In particular, I will divide my talk in two parts. In the first part, I will briefly recall some results on local Ventzel problems. And for these problems, we can manage both the well-posedness results and the asymptotics of the solutions. And in these local Ventzel problems, we have been considering divergence operators, also with drift terms, non-divergence operator, and semilinear operators. And then when passing to non-local Ventzel problem, I shall consider two different types of non-local problems. When I consider fractional operators in space on time and or time, in this case, we have well-posedness and convergence of the solution. While when we shall consider, when we shall consider linear or quasi-linear operators with non-local terms supported on the boundary, while the well-posedness results are fine, it is still an open problem to prove the convergence of the solutions. And then I will give you an idea where are the problems. Okay, so let me start the first part, and let's focus on local Ventzel problems. So the first example of a local Ventzel problem in a fractal domain has been studied in the case of uniform elliptic operator in a joint paper with Gioia Vernole. And we were analyzing this Ventzel problem in a snowflake domain. So as I anticipated you, the snowflake domain is an extension domain, so it is an epsilon delta domain, whose boundary is log 4 over log 3. So it is not an integer number. And of course, when I state this problem is only stated formally because one has to explain what we mean by a fractal Laplacian and what we mean by normal derivative of such a non-differentiable structure. But in any case, this can be handled, and well-posedness results can be obtained. And in this case, we consider also the corresponding Ventzel problems in the so-called approximating prefractal domains. The prefractal domains are polygonal domains in this case, whose boundary have dimension 1. Of course, to analyze the regularity issues of this problem is easier in this case, but what happens when we study the asymptotic behavior of the solution? So we consider different iterations of these polygonal domains and we send h to infinity, is that there is a jump of dimension. And one has to take into account this jump of dimension in this asymptotic behavior. Okay, together with this paper, then we have been considering also non-divergence operator in another joint paper with Regis, Durante, and Vernole. And then in a joint paper with Hinz, Teplaev, and Vernole, we were able to consider also Ventzel problem with a drift term also on the boundary. Actually, we were able to consider a drift term to give a minimum to a tangential derivative in a very, very weak sense also in this framework. And later on, we consider also some semilinear problems with Gioia Vernole, where the semilinearity is both appears both in the bulk and on the boundary. Okay, so which are the key tools that are required to attack this type of problem? So we shall use a semigroup approach, and in order to deal with these irregular domains, we shall need some Sobolev-type function spaces on fractal sets, suitable trace theorem, and green formulas for domain with irregular boundaries, which allow in turn to give a definition of a conormal derivative. And then in order to attack also the semilinear problem, there are suitable techniques which are needed, because usually the domain of the generator of our abstract problem is not known in terms of Sobolev or Bezov spaces. So one has to overcome these difficulties. And again, the presence of the time derivative on the boundary requires us to move to the setting of varying Hilbert spaces in order to consider the asymptotic behavior of the solution. And I hope that to give some details for this later on. Okay, so now let's move and describe the non-local Ventzel problems that I was mentioning before. First of all, let me say that why we are interested in studying non-local Ventzel problems, because the non-local terms appears already in the pioneering paper of Ventzel, but there are also some papers due to Basel-Levin and to Chen and Kumagai in which they are considering non-local term. But there are other different applications where we have non-local terms. For instance, when considering the oxygen diffusion between the lungs and the circulatory system. And going back to the side of the mathematical analysis, besides this paper due to Gall and Varma, in which they point out, they analyze a non-local term on irregular domains, there are these other two papers that I wish to mention, where they are looking at considering non-local problems in irregular domains, but always with Robin-type boundary conditions. So there is not a Laplace-Beltrami operator, let's say, appearing on the boundary. As far as we know, the first paper in which there is also a Ventzel, a full Ventzel boundary condition in an irregular domain is contained in this joint paper with Valles, Santiago, and Vernole, where actually here we were considering a quasi-linear operator, and here is on the boundary appears the analogous, let's say, of the fractal P Laplacian, which can be defined for the snowflake domain. And in this paper, we were considering also this term theta P of U, which is this non-local term. And this non-local term as this structure is a continuous, linear continuous operator from the base of space to its dual, and it has this structure. So up to the term, to the function zeta, this behaves more or less like the seminorm of the base of space BP alpha. And in this paper, we were able to consider well-posedness results and some partial regularity results. But what I want to focus today, is that when P equal 2, so if we consider the case of the usual Laplacian, in that case, one can obtain some regularity results which are crucial in view of numerical approximations. And these regularity results that we have been considering and proving are contained in two joint papers with Creo, Nazarov, and Vernole. And then in another paper, joint paper with Sheffer, Creo, and Vernole, we consider some numerical approximations in terms of finite elements, as I will show you. Okay, so now let's fix the case P equal 2, and let's now consider a prefractal domain. So our issue now is to consider this the regularity results of this non-local Venttsel problem in the case of a prefractal domain. So here now n is fixed, so forgive me, but I was lazy and I decided to call omega our domain. In all this story, eta will be fixed. As I will show you, delta Kn is here the piecewise tangential Laplacian, and theta 2 is a non-local term of order 2, of the same order that we are considering before. So the problem that we want to solve in this case is this one, and it's formally stated here. And to attack this problem, let me introduce the well-known Brezzi-Gilardi spaces, which are the spaces H1 and H2, and the space H1 is usually defined as the set of functions which are continuous all over the boundary and are piecewise H1 on each segment of this polygonal boundary, and H2 is similarly defined. And then the usual weighted Sobolev space H2 of mu, where mu is where r, is the distance from the reentrant corners of our polygonal sets. So the energy function associated to this problem, as the usual structure, is the energy in the bulk plus the energy on the layer plus this term due to the term B plus this term, this term which is due to the non-local term. And with the natural effective domain of this functional is the set of functions H1 with whose trace has finite energy. Here, for the sake of simplicity, I assume that B is continuous up to the boundary and is positive, but these hypotheses are relaxed in our paper. But for the numerical computations, it's easier to understand this. And the underlying measure to attack this type of problem is the usual L2 space, and the measure is the usual Lebesgue measure, two-dimensional Lebesgue measure, plus the arc length. Okay, the term due to the non-local term theta 2 is usually defined in this way, and theta 2 acts as an operator from the space H1 half to its dual. So what one can prove easily is that this form is coercive in its domain V omega Kn. And it is also closed on L2, and thus there exists a unique self-adjoint operator, non-positive operator A, which is the generator of our form. And attached to this operator, there is a strongly continuous analytic semigroup, TP, which acts on L2. So one can consider the abstract Cauchy problem associated to A, where A is the generator of our energy form and U0 is a suitable given datum. And one can prove that under this hypothesis, there exists a unique strict solution. A strict solution means that we have our equation is satisfied pointwise in T, and our function U is C10T with values in L2 and C0T with values in the domain of the operator. Okay, again, thanks to the standard theory of semigroup, we end up, we have an explicit representation of the solution in terms of semigroup. So as I will show you later on, this explicit representation of the solution is a crucial tool when considering the asymptotic behavior of the solutions when n varies. Okay, actually one can prove that the solution of the abstract problem solves our problems that initially formally only stated only formally in a suitable strong sense. Actually, the heat equation in the bulk is satisfied almost everywhere. And at the first iteration, the Ventzel boundary condition is satisfied only in a weak sense in h-1/2. And this is not enough to consider, we don't have enough regularity to consider the numerical approximation. So here is the picture of our domain, and here is a focus on the reentrant corners, which have always, all of them have the same opening, which is 4 pi over 3 in this case. Okay, so what we could prove with a very sophisticated tool, which is called Munchausen trick, is that actually our solution is much better, enjoys much better regularity. Actually, it belongs to the weighted Sobolev space H2 of mu, where mu is greater than 1/4, and I forgot, sorry, it should be less than 1/2. Actually, it turns out to be also order continuous up to the boundary. And moreover, what it turns out is that the extension of our solution, the trace of U, actually belongs to the space H2 of the boundary. So what happens is that this transmission condition, this condition, Ventzel condition, now it satisfies in L2. And to prove this result was crucial in view of our numerical approximation. Because as I showed you before, this domain is not convex. So it's obvious that one cannot expect to have H2 solutions. And so it's clear that the regularity is deteriorated. And if the regularity of the solution is deteriorated, it's well known that also its numerical the rate of convergence in the numerical approximation is deteriorated. But thanks to this result, one can perform a numerical approximation in terms of finite elements space, a finite difference in time, using suitable and dedicated results due to Grisbar, one can prove a priori error as optimal a priori error estimates. So I will not go into details to give you details on this, but what I want to tell you is that this regularity result allowed us to prove optimal rate of convergence. So we obtain an optimal rate of convergence with the finite element scheme, like the one that you would obtain when considering, for instance, H2 functions or convex domains. So I don't want you to bother with all these stuff, but only I want to show you only some pictures. So we consider, for instance, we choose as a source term this function f, which is located inside our domain omega, where we decided to put a local term only on this blue part of the boundary, and on the other part there was the usual, there was no local term. And what we could prove is that actually the heat starts diffusing within the bulk and is captured by the layer, and some part of the streamlines pass through, of course, as it must be on the across the boundary. Now the story is, can we solve this problem in a regular domain? The answer is yes, and the answer is contained in the paper, joint paper with Velez, Santiago, and Werner. But now the story is, can we study the asymptotics of the solution? Can we prove that the prefractal solution do converge to the limit fractal 1? This was an open problem up to some time ago, but then we recently realized that using some recent results contained in a joint paper with Creo and Hinz, maybe this problem of considering the asymptotic of the solutions of Ventzel problem with a non-local term on the boundary can be solved. But we have to finish investigating this result. And what I want to say is that the regularity of the prefractal solutions, so in polygonal domains for the case P different from 2, is still open. So the non-local term on the boundary can create some problems in the asymptotics. But let me go ahead and now move to another Robin Ventzel problem of no local type. So this Ventzel problem that we've been investigating is a non-local problem, because here appears a regional fractional P Laplacian that I will define in a while, and on the boundary appears a non-local term which plays the role of a fractional, regional fractional P Laplacian supported on the boundary. That's why we decided to call it Robin Ventzel problem. And here appears this term, which will be what we shall call the P fractional normal derivative on the boundary. So in a joint paper with Vernol and Creo, first we analyzed the case in which the non-local term was not supported on the boundary. And for this type of problems, so without the non-local term, we were able to prove well posedness result and to study the asymptotics of the solution. And recently, later on with Creo, we investigated the full problem with the non-local term on the boundary. And for this type of problem, we are able to consider well posedness results and to prove ultra-contractivity results of the associated semigroup. So let's see briefly what's the fractional P Laplacian. The fractional regional fractional P Laplacian has been introduced by Varma in 2016, and he was working also obtaining many results also in the framework of Lipschitz domains, and is defined as the principal value of this integral whenever this limit exists. So, oh, sorry. Sorry. Doesn't take the command anymore. I don't know why. Sorry. Okay. Okay, and the term theta p gamma is again the non-local term of the same type that we analyzed later. But in order to describe the role of the non-local term in the asymptotics, let me stress the fact that when the non-local term, we neglect the non-local term on the boundary, actually one can prove the convergence of the solutions. And so let's confine ourselves to this simple case. And again, let's consider the snowflake domain, omega, with boundary k. And let's formally state this problem, which now becomes a Robin type problem. So you see that the non-local term of the boundary has been neglected. Okay, then we shall consider in the corresponding approximating domain omega n, the corresponding Robin Ventzel problems. And you see here in red appears some positive constant, which will play a crucial role when studying the asymptotics. And we shall come over this later on. Okay, so how do we proceed? We introduce the energy functional associated to our problem, which we call capital phi, and in the space L2 of omega m, where m is the Lebesgue, two-dimensional Lebesgue measure, plus the d measure mu supported on the snowflake k, and we consider the corresponding approximating domain phi n. So now the slightly difference is that the corresponding measure which we are considering are the measure mn, which vary, have a factor, a positive factor here, delta n, which has a crucial will have a crucial role again, the same delta n which appears in the problem, which will have a crucial role in the asymptotic behavior. Okay, so what we can prove is that our functional phi is weakly lower semi-continuous, proper, and convex, and its subdifferential is single valued and maximal monotone and accretive. And the opposite of the subdifferential generates a nonlinear semigroup, which is strongly continuous and contractive. So one can consider this abstract problem, and under a suitable assumption on F, one can prove the existence and uniqueness of a stronger solution. Once we have done this, we can consider and prove that actually this solution solves the problem that we had initially formally stated in this, let's say, weak sense. And this result can be achieved using a characterization of the subdifferential and using a p-fractional green formula that we have been proving. So let me say a couple of words on the p-fractional normal derivative that we defined. Note that, of course, this transmission condition is solved in a very weak sense, in the sense of the dual of the Bessel space. So what we did to introduce the fractional normal derivative was to propose a different definition from the one given in Varma on p-fractional normal derivative in the Lipschitz case. And actually, we introduce the space capital V of the set of functions WSP whose Laplace, p-fractional Laplacian belongs to LP prime in the sense of distribution. And we say that the function U admits a p-fractional normal derivative if there exists a function G in the dual of this Sobolev space, such that this equality holds. Once that we have this definition of p-fractional normal derivative on Lipschitz domains, we were able to prove the following theorem, that one can define a p-fractional normal derivative on the fractal set, of the boundary of the fractal set, via a green formula. So the first step was to prove a p-fractional green formula for fractal boundaries, and this was achieved by using limit arguments, in a sense that we exploited the fact that omega can be approximated in terms of Lipschitz domain omega n, and then by passing to the limit suitably, we were able to prove this green formula. And then I want to stress the fact that this definition is consistent with the usual notion of green formula that we gave with Bernoulli in 2013, because when S goes to 1, actually we recover the usual green formula for fractal boundaries. Okay. Okay. So the same procedure can be applied to prove the existence of a weak solution in the case of the prefractal domains. Now it comes the question of wondering whether the prefractal solution do tend to the limit fractal 1. And in order to do this, we shall prove these results in the case of homogeneous problems. We shall go via the convergence of the energy forms. And in particular, we shall use the notion of M convergence introduced by Moscow in the late 60s, and then generalized by Guai-Xioi et al. To the setting of varying Hilbert spaces. So what we can prove actually is that under a suitable choice of our factor delta n, one can prove the M convergence of the functionals, and this in turn allows us to prove the convergence of the solutions. This is due to the fact that actually the M convergence of the function, the energy functionals is associated to is equivalent to the G convergence of the subdifferential, and the convergence of the subdifferentials allows us to prove the convergence of the associated nonlinear semigroups associated to our problems. So,
Maria,
yes.
The quantity 3/4, is it rigid or not?
It's rigid in the sense that it depends on what we call the structural constant of the fractal. So it's in the case of the curve is 3/4. If you move to other slightly different fractals, it depends, because for instance, this 3 is the inverse of the contraction factors that you find in the Koch curve. Yes, when you consider the similarity mappings, the contraction factor is 1/3, and this 4 is connected to the fact that we are considering 4 contractive similitudes. So it's rigid at this stage.
Okay.
If you change fractal, you will end up with a different scaling factor.
Okay. Thank you.
Okay, so the asymptotics is fine for let's say non-local operators, but only supported on the bulk. Let's see some possible generalizations that we have been dealing with recently. And recently we considered non-autonomous Venttsel-type problems, so of fractional type. So this operator B, I will not define for to save some time, is a generalization of the fractional P Laplacian in the non-autonomous framework. And here again, we have coupled with the Venttsel-type condition. And again, here we have a non-local term of fractional type, which is still non-autonomous. And by the way, this problem is also semi-linear. And what we were able to do in this framework, in the framework or non-irregular domains, here we were in the general framework of extension domains, is that we consider a suitable energy, non-autonomous energy form E, which admits a generator ADT with domain which is depending on time, but it enjoys some key properties, which allows us to prove that there exists an evolution family of operators U. And thanks to this, we can prove actually that this allows us to give a strong interpretation of the problem in a suitable base of spaces. And moreover, we can prove also ultracontractivity of the associated evolution operators. And you see that the exponent in the ultracontractivity, this lambda, depends both of the embedding space Rn, but also on the fractal dimension D of our boundary. I want to stress the fact that in the non-autonomous case, we do not have results on the asymptotics of the solution, because usually when we have we can prove the asymptotics results by proving the convergence of the associated semigroup, let's say, and using the representation of the solutions in terms of the semigroup. But unfortunately, this result relies on the Trotter-Kato theorem for the semigroup. But unfortunately, for the evolution operators, to our knowledge, there are no results. So if somebody can suggest me a reference when we can find something similar, it would very important to know this. So the asymptotic in the non-autonomous case is completely open issue. And then, at least, I want to stress that we, as I promised, have been considering also a non-local Ventzel problem when the non-locality is due to the presence of a fractional time derivative. Actually, here we were considering this non-local Ventzel problem where we had the time fractional Ventzel problem, let's say, and note that the fractional derivative appears both in the bulk and both in the boundary. And here we are, omega is the snowflake, but it could be any reasonable, let's say, set with a reasonable fractal boundary. And the fractional normal derivative, for the definition of fractional normal derivative, we refer to the notion given by Gall and Varma in their book. Actually, here f is a continuous function in 0t, and we assume that this integrand is in W11. See, this notion of that they've been using is interesting because it's weaker with respect to the notion of Caputo derivative given by Caputo himself. But this notion, for instance, allows to prove that the derivative of constant function is 0. But in any case, in order to attack this problem, we introduce the usual energy form associated to our problem with its effective domain. And we introduce we consider the abstract Cauchy problem where A is the generator, of our energy form. And under suitable assumptions on F and U0, one can prove that there exists a unique strong solution of this problem, which has this representation formula. So this S alpha involves the semigroup here, in its representation are the solution, the so-called solution families. And this P alpha is a more complicated expression, and it involves the what is called the right functions. So for this problem, we were able to prove again that the solution of the abstract problem solves our formally stated problem in a suitable weak sense. And similar results can be obtained in the case of prefractal problems. Okay, and again, by usually the same techniques, more or less, one can prove that the weak solution solves our problem in a weak sense. And then what we were able to prove again is that the prefractal problems homogeneous prefractal problems, P0N, have weak solutions which converge to the limit fractal 1. And again, here the asymptotics in this case is possible because we take advantage of the fact that the solution family S alpha is expressed in terms of the semigroup. And so, but if one wants to move to the non-homogeneous case, the situation becomes much more tricky, and there's still an open problem to manage the asymptotic behavior of the solution in this framework. And so now we are investigating the well-posed result for non-autonomous fractional type operator of Venttsel-type, and with a special focus to ultra-contractivity results. But here there are a lot of constraints, and we are still investigating this problem. And as I was telling you, the asymptotics of the solution when the non-local term is supported on the boundary seems to have a positive answer now, thanks to this paper with Hinz and Creo. And then we are trying to analyze recently, this is a work in progress, also some results on the asymptotics of inverse problems. But here we are at the very beginning, so this is a joint paper with Gianluca Mola, Creo, and Silvia Romanelli. And,
excuse me, SC is Simona just.
SC, sorry, C. Oh, sorry, yes. C, sorry. It's Creo, yes. It's clear that I made the cut a copy and
Okay.
I forgot. Okay, yes. That's it. And I thank you for your attention. I think that I can stop here.
Well, let's thank our speaker.
Thank you for for listening to me.
Well, please comments or questions. In fact, I have a question, even Tremedze, a question. When you talked about contractivity, you had a quantity lambda, yeah? Which drives this how fast is it?
Yes, the decay of the semigroup. Yeah,
yes.
Here of the evolution family. Here we are talking about the evolution.
Yeah, this D is the dimension of the boundary.
Yes.
Yes. So the more fractal it is, the larger should be the S.
Yes.
S anyway should be greater than 1/2.
Yes.
Yes. And the more fractal is your domain, the larger should be S. In general, it should be close to 1. Am I right?
Close to 1 who? D or
no,
what?
S.
S, yes, yes.
Mm-hmm. Okay, and another question is about applications or where from such problems arise. Could you send me your references, because I know some of them, but I think not all of them.
Okay, for the applications, yes. I hope to have the files, still to have the electronic version of the files, but at least the references of the paper, of course.
Okay, okay. Yeah, more comments? If not, let's thank our speaker again. And now,
Thank you.
please switch off your
Yes.
sharing. Oh, well.